Hello, my name is Vladimir Korikov, and this is the Domain-Driven Design in Practice course, starting with the first bounded context. In this module, we will begin the actual development process. We'll start off with the basic functionality for our model of a snack machine, inserting coins and notes to the machine and returning the money. You will see how entities differ from value objects and learn the best practices for working with them. Before we start, let's take a minute to define the terms we'll be using in this course. You might have seen many of them in the past, but it's not always clear what they mean in different circumstances. First of all, I use the terms problem domain and domain interchangeably. They mean the actual problem our software is going to solve, the purpose it is built for. The term core domain is a subset of these two. It is the essential part of the problem domain, the part which cannot be delegated to an external solution and must be resolved by us developers. Also, the terms business logic, business rules, domain logic, domain knowledge, and domain model are synonymous. You can think of them this way. The business logic you enclose in your code represents the knowledge that you as a software developer have about the problem domain. You express this knowledge by codifying a model of the domain you are working in, hence the term domain model. The business logic of an application typically resides in the two innermost layers of the inner architecture. I refer to the notions from these two layers as domain classes. So a domain class might be a repository, an entity, and so on, but not an application service. We will talk about the application services in the next module. The first bounded context we will start with is snack machine. We will talk about the ways to represent bounded context later in this course. For now, we will focus on the machine model implementation. Our first task will be to model the way it works with coins and notes. So what are the operations we should be able to perform with money? Obviously, we need a way to insert them into the machine. Also, if we change our mind, then we should be able to take the inserted money back. And finally, we may want to buy something. In this case, the amount of money we inserted should go to the machine permanently, and we should get back the change. We will take a shortcut in this module and implement a simplified version of the purchase functionality. We will extend it in the future modules. We'll start the development with the core domain, the model of the snack machine. Here's the solution for our application. I named it DDD in practice. You can see there is only one project currently, named Logic. In it, we will store our business logic, utilities, and data access code. This is the class for the snack machine. Note the use of the sealed keyword. It's a good practice to give your code as few privileges as possible by default. So, to insert money to the snack machine, we need to have a place where the coins and notes will be stored. The easiest way to do this is to introduce separate properties for each type of coin and note, so that we know exactly how many of them are in the machine right now. You can see here a separate property for the number of 1-cent coins, quarters, and so on. The actual method then could look like this. We accept any amount of money and just add them to the money we have in the machine. So far so good. The second function our snack machine should have is the ability to return the money we inserted in case the user changed their mind. This raises a problem as we don't distinguish the money the user inserted from the money that was in the machine beforehand, so we can't say how much money we should return to the user. The solution here is to introduce a separate set of properties which would define the amount of money that is currently in a transaction. This is the money the user will be able to get back or use to make a purchase. When the user inserts a coin or a note, this money is added to the money in transaction instead of the money that belongs to the machine, so we need to change the insert money method, like this. The return method then just returns all the money that the user inserted. We can model this behavior by nullifying the corresponding properties. And finally, we should be able to buy a snack. For now, we can depict it like this. Just move all the money in transaction to the money inside the machine and nullify the transaction money after that. Alright, let's overlook this implementation again. There is a concept here which can be extracted out of the snack machine class. I bet you already guessed that it's the notion of money. Indeed, we have two identical sets of properties. They represent the money the machine has, the amount of money inside, and the amount of money inserted by a user. We can introduce an abstraction, a new class called money. And now we are able to move all the money-related members to this class, and also add an addition operator to it. What this operator does is it introduces a plus function. It takes two money instances and creates a new one which consists of all coins and notes from the original two. Now we are able to add just a single property, money inside, and remove all these properties from here, and another one for the money in transaction. The insert money method can also accept a money instance instead of the separate count parameters. Here we make use of the plus operator we introduced in the money class. For the return money method, we will also need to introduce some operation for clearing up the money instance to show that there is no longer any money in the transaction. We will talk about it later. For now, I'll just comment this line out. For the buy snack method, we are moving all the money in transaction to the money inside and also nullifying the instance. You can see here, after we brought a new concept, money, the code of the snack machine became much simpler. This is no coincidence. You will see that introducing a new abstraction often makes the overall solution easier to understand and maintain. Let's recap what we came through in the previous demo. First of all, you saw we started with the core domain right away, without modeling the UI or the database first. It's a good idea to always do this. You should always begin the project by experimenting with your domain model, as it's the most important part of your application. Secondly, always start with a single bounded context for all business logic in your application. Don't try to divide it into several pieces upfront. While bounded contexts help reduce complexity of your code, the application is justified only when your code base is quite big already. Otherwise, they won't reduce the complexity, but rather increase it instead. And thirdly, constantly evaluate your code and look for hidden abstractions. You saw that after we introduced the money class, the code of the snack machine was simplified greatly. In our case, the presence of this abstraction was pretty obvious, of course, and it's not always possible to identify one in a more sophisticated situation. Nevertheless, if you see your code becomes awkward, you should test different approaches and examine if they fit your problem domain. It might be there is a hidden abstraction in your domain model that you didn't express just yet. At this point, we approached an important topic, the difference between entities and value objects. In our codebase, we currently have two classes, snack machine and money. They seem pretty similar to each other, but their semantics differs significantly. The snack machine class here is an entity, whereas money is a value object. Let's elaborate on that. The main difference between entities and value objects is in the way we identify them. There are three types of equality when it comes to comparing objects with each other: reference equality, identifier equality, and structural equality. Reference equality means that two objects are deemed to be equal if they reference the same address in the memory. Identifier equality implies a class has an ID field. Two instances of such a class would be equal if they have the same identifiers. And finally, with structural equality, we consider two objects equal if all of their members match. So how does the way we identify entities and value objects differ? The difference here is that identifier equality refers to entities exclusively, whereas value objects possess structural equality. In practice, it means that value objects don't have an identifier field, and if two value objects have the same set of attributes, we can treat them interchangeably. It makes a lot of sense if you look at the notion of money in our domain model. If we have two $1 bills, it doesn't really matter which of them we work with. We don't care about their identity. We can easily replace one set of coins and notes with another one, as long as these two sets have the same composition. At the same time, even if two snack machines have the same amount of money inside, we don't treat them interchangeably. We do care about which of them we work with. You can think of it in a similar way you would think of two people bearing the same name. We don't treat them as the same person because of that. They have their own inherent identity. Another distinction between the two notions is immutability. Value objects should be immutable in the sense that if we need to change such an object, we construct a new instance based on the existing object rather than changing it. On the contrary, entities are almost always mutable. The next difference is that value objects cannot live by their own. They should always belong to one or several entities. In our application, money doesn't make sense without a snack machine. If it does, the money class would be an entity itself. We can put it another way. There always should be at least one entity that owns a value object. Again, in our case, it is the snack machine class, which contains two properties of the money type. An important implication from this point is that value objects don't have their own tables in the database. We will talk about it in more detail in the next module when we'll be discussing persistence for our domain model. It's not always clear if a concept in your domain model is an entity or a value object, and unfortunately there are no objective attributes you could use to get to know it. Whether or not a notion is a value object fully depends on the problem domain. A concept can be an entity in one domain model and a value object in another. For example, in our system, the money class is certainly a value object. At the same time, if you build a software for tracking the flow of the cash in the whole country, you do need to treat every single bill separately, as you need to gather statistics for each of them. In this case, the notion of money would be an entity, although you would probably name it a note or bill. Despite the lack of objective traits, you can still employ some techniques in order to attribute a concept to either entities or value objects. First of all, you should take into account the notion of identity we discussed previously. If you can safely replace an instance of a class with another one, which has the same set of attributes, that's a good sign this concept is a value object. A good way of thinking of value objects is comparing them to integers. Do you really care if the integer 5 is the same 5 that you used in the previous function? Definitely not. All 5s in your application are the same regardless of how they were instantiated. That makes an integer essentially a value object. Now ask yourself, is this notion in your domain looks like integer? If the answer is yes, then it's a value object. In our application, we don't really care where the instances of the money class come from, and they are really similar to integers because of that. All said above has an important implication. Always prefer value objects to entities. Value objects are mutable and more lightweight than entities. Because of that, they are extremely easy to work with. Ideally, you should always try to put most of the business logic into value objects. Entities in this situation would act as wrappers upon them and provide more high-level instructions. Also, it might be that a concept you saw as an entity at first essentially is a value object. For example, an address class in your system could be introduced as an entity initially. It may have its own ID field and a separate table in the database. But after revisiting it, you might notice that in your domain, addresses don't actually have their own identity and can be used interchangeably. In this case, don't hesitate to refactor your domain model and convert the entity into a value object. A typical application contains a lot of entities, so there should be a base class where you can gather common behavior for each of them. Let's discuss different approaches for creating such a base class. The first option we have here is to introduce an interface like this. That way, we would be sure all domain entities in our model have some minimal functionality, the ID property. Although it might seem a good decision, in most cases having an interface as a base entity is a bad idea. First of all, interfaces don't allow you to gather any logic in them. You need to implement this logic yourself, which leads to a massive code duplication. Even in this example, you need to create the ID property in every single entity, which is a heavy violation of the don't repeat yourself principle. Secondly, the use of an interface doesn't show the appropriate relationship between domain entities. Implementing an interface means that your class makes a promise to have some functionality defined in the interface. Two classes implementing the same interface don't tell us anything about their relationship. They can be related, but it also can be that they belong to entirely unconnected hierarchies. In other words, the iEntity interface introduces a can-do relationship, whereas domain entities should be connected to the base class by is-a relation. Not only such classes should have common functionality, but they themselves are entities. The only way for us to avoid these drawbacks is to introduce an abstract base class.
Oh, y se cayó. ¿Ese es tuyo?
Here's the actual code
Tuyo,
for the
pues,
entity
hija.
base class. You can see it contains
No
an
lo
identifier
botes.
and equality
Recoge.
operators. Let's walk through it together. As we discussed earlier, entities have their own inherent identity. The best way to represent this identity is to introduce a separate member, the ID property. It's a good idea to use a long type for this purpose by default, as such IDs are easier to work with than, say, GUIDs. The equality members consist of 4 methods. The equals method is defined in the base object class and is often used by .NET internally. For example, when we call the contains method on a list of entities, a .NET base class library compares the objects inside the list with the target one by calling the equals method. The default equals implementation gives us only reference equality. As we discussed earlier, entities also possess the identifier equality, so we need to override this method in order to introduce it. Here's how it looks like inside. We try to cast the other object to entity, compare the two references to each other. That gives us the reference equality. If the type of the entities is not the same, they cannot be equal no matter what IDs they have. Also, if any of the identifiers is 0, it means that the ID was not yet set to the entity, and we cannot compare it to other entities because its identity is not yet established. And finally, if all previous checks are passed, we compare the identifiers themselves, which gives us identifier equality. Aside from the equals method, it's also a good idea to define the equality operator, so that we can use it in our code like this. The only difference between the equality operator and the equals method is that the former can accept nulls for both operands, hence these checks here. You can see if both of the parameters are null, we return true. After that, we can call the equals method we implemented earlier. The inequality operator is very simple. It just calls the equality operator and reverts the result. Finally, we also need to implement the getHashcode method. It's important for two objects which are equal to each other to always generate the same hashcode. Here, the hashcode depends on the object's type and identifier, which are the parts of the object's identity. If you want to learn more about this method, check out this great Stack Overflow answer. Some developers also implement the IEquatable interface on the entity class like this. You can see that the equals method just converts the object parameter to the entity type and calls the new method. I tend not to do that because this interface was designed for the use in value types, structs in other words, and doesn't provide any additional value in classes. Therefore, its usage here violates the Yagni principle. You might have noticed that we don't set the ID property anywhere in this class. We will talk about it when we'll be discussing persistence for our domain model in the context of object relational mappers. Now, as we have the entity base class, we can inherit our snack machine from it. This is our first fully fledged entity. In this demo, you saw the entity base class we'll be using in our application. It's important to remember that, unlike value objects, each entity has their own identity. The best way to introduce this identity is to put it into the base class. The additional benefit here is that we are able to implement all required equality members in a single place. All entities in our domain model get them for free just by inheriting from the base class. Value objects don't have their own identity, and thus they shouldn't have the ID property like entities. It also means that we cannot place all code required for equality in a base class. In order to implement structural equality, we need to know the internals of each value object class. Nevertheless, we can still gather some logic common to such classes. Here's the code of the value object base class. You can see that we do override the equals method, but delegate the actual work to the abstract equals core method. And the same is for getHashcode. We could just leave the equals and getHashcode methods without overriding them here, but this practice has two advantages. First, the new two methods are abstract, meaning that we won't forget to implement them in a derived value object class. The compiler will notify us about that. Second, we are making sure that the object coming to the equals core method is of the same type as the current value object, and it is not null. Thus, we don't need to duplicate these checks in the derived classes, we can just gather them here. The equality and inequality operators are the same as in the entities. Now, let's look at how we can use this class. We can derive money from it, and you can see as soon as we introduced the inheritance, the compiler tells us that we need to implement the two abstract methods. So let's do that. For the equals core method, we need to check the equality for each of the properties. And the same goes for the getHashcode method. All members of the value object should take part in the hashcode generation. Alright, let's reiterate it once again. The most important distinction between entities and value objects is the difference in the way we identify them. There are three types of equality. Reference equality belongs to both entities and value objects, identifier equality to entities, structural equality to value objects. This means that each entity should have their own identity, which is best expressed using a separate ID property. It also means that we can create a single equality method that would feed every entity. Value objects at the same time don't have an identity, so they cannot have a separate ID field. The structural equality means that we need to implement the comparison logic in each value object class apart, but this task can be alleviated by factoring some common logic out to the base class. .NET has a notion with a similar name, value type. The value type class is a base class for enums and primitive types like int, byte, and so on. Also, all structs inherit from it. Strictly speaking, there is no relation between DDD value objects and .NET value types, because the former is a design concept and the latter is a technical implementation detail. However, there are some similarities in them. Value types in .NET are easy to make immutable, and they implement structural equality instead of reference equality. In theory, you could use .NET value types to represent value objects in your domain model. In practice, however, this is not the best solution. Structs don't support inheritance. Because of that, you will have to implement equality operators in every struct separately, which would lead to code duplication. Also, structs don't interact particularly well with object relational mappers. Therefore, despite the semantics likeliness between these two notions, we are better off using classes to implement value objects in our domain model. In the previous module, we talked about unit testing in the context of DDD. We discussed that we should cover with unit tests only the innermost layer of the onion architecture: entities, value objects, aggregates, and domain events. Now let's talk about when we should write unit tests. The process of test-driven development proposes that we employ the test-first approach. While it's true that TDD has a lot of benefits, in my opinion, both test-first and code-first approaches are applicable in different circumstances. You can read about it in more detail in my blog post here. In short, there are basically two modes in which we write code. With the first one, we are pretty sure what we want the code to do, so we can create unit tests upfront, before we actually start implementing the required functionality. On the other hand, we might be exploring new areas in our domain model. When experimenting with different ideas in code, we are not exactly sure how the implementation should look like. In this case, we are better off not trying to come up with unit tests upfront and just write the code without them. The reason is that while experimenting, we often rewrite our code and even throw it away completely, and unit tests would only slow us down with that. You saw that we wrote the first draft of our domain model without any tests. We were experimenting with code, and that resulted in a new concept, the money class, emerged. Now, as we are finished with the experiments, we are pretty sure about how the code should look like. It is time now to enter the test-first mode and continue the development adhering to the TDD process. Let's start off by adding a new Visual Studio project for unit tests. Good. I'm gonna use XUnit as the test framework for our application, but other test frameworks would fit as well, of course. Also, we'll be using Fluent Assertions. It's a library that helps write assertions in a more fluent way. That's pretty handy as it increases test code readability. Alright, you can see here our two NuGet packages with their dependencies installed. I also use ncrunch as a test runner. It runs unit tests constantly on the background and gives a nice visual feedback in case something breaks. It's a paid plugin and it's absolutely fine if you don't have it. You can achieve the same result by running your tests manually. You will see how ncrunch works in a minute. We will begin with the money class. Let me rename this class created by Visual Studio to MoneySpecs. Perfect. I'm gonna start by covering with unit tests the existing functionality. So the first test would verify the summing function. Let's call it sum of two monies produces a correct result. Okay, so what we're gonna do here is we are going to create two money instances, sum them up, and verify the resulting money instance contains the correct amount of coins and notes. Here's how we could write an assertion using the standard assert equal syntax, but we'll use fluent assertions for that. You can see this version of the same assertion mimics the English language in the sense that it reads from left to right just as a regular sentence. That's basically it. This is the only reason why we use this library for our tests. It makes our tests a little bit more readable. Alright, here are the other 5 assertions. As you can see, we are checking that all properties in the money instance were summed up correctly. These green circles here, produced by nCrunch, they represent the test coverage. If we go here and replace one of the parameters with 0, you can see nCrunch tells us the implementation now doesn't comply with the unit test. And here is the exact line that checks that. This plugin is pretty useful as it helps eliminate the manual work required for running unit tests after each change, but again, it's perfectly fine if you just run them manually. Just don't forget to do that often enough so that you get rapid feedback. I'm gonna employ the classic 3A test structure for this course. You can see this section here is the range section. The following two are act and assert. I usually don't write those comments and just separate the sections with a blank line. The other already existing functionality we need to test is the one that regards to equality. It's a good practice to always check that two value object instances with the same data of the same type are considered to be equal, because, as we know, .NET employs the reference equality for all classes by default. Let's make sure the money class has the structural equality. Let's name the test two money instances equal if they contain the same money amount. So basically what we want to do here is we want to create two instances like this and verify the first one is the same as the second one. Again, we use Fluent Assertions library for this, which calls the equals method behind the skin, and we'll also check they have the same hash code too. Good. With another test, we will check that two money instances don't equal if they contain different money amounts. So let's create a dollar first, and then 100 cents. The dollar, although it has the same value, shouldn't be equal to 100 cents, because in our domain model we do need to distinguish such things. The hash code should differ as well. Alright, now as we are done with the existing functionality, let's think about what other methods we need from the money class. The first thing to ponder should always be the edge cases. What are they in this particular case? For example, can we create a money instance with no value or with -1? The empty money instance does make sense in our domain model. After all, the snack machine we are modeling can have no money inside at some point. On the other hand, a negative value doesn't make sense and should be prohibited. So let's create a test for that. I'll name it cannot create money with negative value. This would be a parameterized test. Basically what we are doing here is we are trying to pass a negative count to each of the parameters the constructor has. Hence we need to exercise all parameters one by one. To verify they all fail, I'm gonna define an action delegate. And check it throws an exception. You can see the test fails. That's because right now nothing prevents us from creating illegal money objects. Let's fix that. If 1 cent count is less than 0, then we should throw an invalid exception. And we need to replicate this validation for all parameters. The test is passing now, very good. At this point, it is pretty clear we will need at least 2 more methods from our money class. Obviously, we will need to get the value a money instance represents, so that we are not forced to calculate it manually all the time. Also, it is logical to have a subtraction operation along with the addition one, so we need to implement it as well. I need to make an important warning here. Always follow the Yagni principle and refrain from adding any functionality upfront. Remember, this principle is one of the most important, and you should always adhere to it when developing software projects. It might seem that by adding these 2 features to the money class, we are violating this principle, because they are not used anywhere in our domain model yet. But I'm taking a shortcut here. I know that we will need them in the near future, because I already went through the development of this application. In a real-world situation, you should always try not to introduce any code until you see that you cannot solve the task you are working on without it. Alright, so let's add another test here. We can name it Amount is calculated correctly. This also would be a parameterized test, so that we would be able to run it against a set of different use cases. Here they are. You can see that, for example, when we create an empty money instance, we expect its value to be 0. For a single cent it would be 1 cent, and so on. Basically, I'm just throwing a pile of cases I calculated manually, creating an instance, and verifying the amount it represents is equivalent to the expected amount. At this point, we don't have the amount property yet, so let's add it. Following the test-first approach, we need to make sure our test fails before implementing the required functionality, so I'm writing the simplest implementation possible just to make the application compile. The letter M here means the literal value is of the decimal type. The test fails as expected, and crunch shows that one of the use cases expects the value to be 500 but received 0 instead. The actual implementation is pretty simple. We just need to sum up all the coins and notes the money instance has, taking into account their denomination. And you can see all tests are passing now. It's a good time to make some refactoring for our code at this point. You can see the properties of the money class has public setters, which means that they can be easily changed by the external code. Remember, one of the attributes of value objects is that they should be immutable. To implement immutability, we could just hide the properties from the outside world by making them private, like this. But I'm using C#6 here, so I can use one of the latest features it introduces, read-only properties. To implement a read-only property, I just need to remove the setter, and here we are, our class is now completely immutable. Another feature C#6 adds is Expression-Bodied Members. It's a good idea to use it for the amount property. Perfect. The last method we need to implement is the Subtraction Operator. Let's add a test. Subtraction of two monies produces a correct result. So basically what we need to do here is we need to take two instances and subtract one from the other. The resulting money instance should have the correct counts for each property. An important edge situation in this case is that we can try to subtract more than we have, so we need to make sure we prohibit such operations as well. I name the test cannot subtract more than exists. Declaring two instances, note that the first one has only one 10-cent coin, and the second one contains a single cent. We cannot subtract one from the other because there are not enough coins to perform such a subtraction, so we need to make sure such operation throws an exception. Alright, so just as before, we are implementing the test in the simplest and obviously incorrect way, just to make sure the tests fail. And you can see they do fail at this point. This unit test, for example, expects 9 but gets 0 instead. What we need to do here is we need to subtract every single property from each other. This makes the test pass. Perfect. Let's start implementing the snack machine with the simplest method, return money. Creating another file, snack machine tests. We can call the test return money empties the money in transaction. I create a snack machine here and insert a $1 inside. And you can see the test doesn't like what we've done here so far. The problem is that we are trying to use the money in transaction instance without initializing it. That's one of the benefits continuous test running provides us. We get the feedback very quickly. Alright, so let's add a constructor, assign an empty instance to the money inside, and the same for the money in transaction. Good, the tests went green again. Calling the return money method and verifying the amount of money in transaction is 0. The test fails, and now we need to implement the method itself. Here we need to somehow clear the money that are currently in transaction. The first option that could come to mind is to introduce a clear method and call it here like this. This solution is not the best one, as it violates the immutability of the money class. In order to implement such a method, we would need to change the state of the existing money instance. A better way of dealing with it is to just overwrite the instance with a new one, like this. This way, we are keeping the money value object immutable. You can see the tests are passing, so now we can do a bit of refactoring. First of all, creating a money instance and passing all 6 parameters to it all the time is a bit annoying. As our money class is a value object, it's a good idea to create a static read-only field for the empty money instance. Here it is. Now we can replace the constructor with this field. And it turns out we can create a field for each coin and note as well. Cent, 10 cent, quarter, and so on. This enables us to simplify our test like this. Another thing we can do here is we can employ the new features of C#6 and simplify our code even further. Static using statements allow us to import a separate class and use its static members without specifying the class name. So money.dollar here turns to just dollar. And we can do the same in the snack machine class. Another C#6 feature is property initializers. I can just assign the money instances the initial values and remove the constructor. Alright, another method we are going to cover with tests is the insert money method. We can call the test inserted money goes to the money in transaction. Creating a new snack machine, inserting a cent and a dollar, and checking the amount of money is correct. The test passes because we already implemented this functionality, but let's make sure the test doesn't give us false positive by commenting this line here. Very good, I can uncomment it back again. At this point, we need to once again think of possible edge cases. Is it possible to insert not a single coin or note, but several of them all at once? That is probably a question we need to ask the domain expert, because at this point it's not obvious if the model we are building should support such a use case. Remember, communication between the developers and domain experts is vital, and the domain-driven design practices put a great emphasis on this part of the development process. Let's say that we, together with domain experts, decided our domain should only accept a single coin or bill at a time. That makes sense because that's how a real snack machine's receiver works. So we need to add another test to verify that. Cannot insert more than one coin or note at a time. In the test, we need to create a 2-cent money instance and try to insert it to the machine. The test would pass if the machine throws an exception. Alright, to implement this, we need to specify all possible values we accept in the insert method and check if the incoming instance is one of them. Good. And finally, we need to finish the buy-snack method. We can add a test named money in transaction goes to the money inside after purchase. Here we are inserting $2 to a machine, calling the buy-snack method, and checking the money in transaction is empty and the money inside contains $2 after that. The implementation is pretty simple, we just need to assign the money inside instance an empty value here. We are done with the first draft of the snack machine. It obviously lacks some significant parts, for example, the buy method should definitely deal with snacks somehow and not just take all inserted money. We will address this in the later modules when we'll be discussing aggregates and repositories. Also, in a real-world application, you would probably want to write more unit tests. For example, it's a good idea to check that a newly created snack machine doesn't contain any money in it. But I'll leave it aside just to keep our development process less verbose. In the previous 3 demos, you saw how we implemented our first version of the money and snack machine classes. Note that we kept the money value object immutable. Whenever we needed to perform such operations as addition or subtraction, we created a new instance of the class without changing the existing ones. The snack machine entity, on the other hand, is mutable. Mutability is an inherent trait for all entities. They change their state throughout the lifetime while maintaining immutable and unique identity. Also note that the snack machine entity contains not as much logic comparing to the money value object. All it does at this point is delegates most of its operations to the money class. This is another good practice I mentioned earlier. Always try to delegate as much logic as possible from entities to value objects. Value objects are easier to maintain because of their immutability. During this phase of development, we stuck to the TDD process, meaning that we wrote the tests first and then implemented the required functionality according to those tests. I intentionally demonstrated the whole process to show you how nicely domain-driven design can be combined with test-driven development. In the next modules, however, I will depart from adhering to the test-first approach just to speed our development up. But keep in mind that it's a good practice to follow this simple rule. Write the code first when you are experimenting with your model and switch to the test-first mode when you have a good picture of how the code should look like. And of course, while the test-driven development practices can be beneficial, you don't have to follow them in order to do domain-driven design. But remember to always cover your domain model with unit tests, regardless of when you prefer to write them. In this module, we started the development with the first bounded context, which is snack machines. We focused on entities and value objects. You learned the differences and best practices behind these two notions. Let's reiterate through the most important moments of this module. First of all, try to begin the development by working with the core domain first. Your core domain, along with the unit tests covering it, is the most important part of the application you are building. Secondly, always start the development with a single bounded context. There is little value in dividing your application into several pieces up front, as you usually don't have enough information to make a competent decision about the proper boundaries at this point. Constantly evaluate your code and look for hidden abstractions in it. If you see your code becomes unclear or convey its meaning vaguely, it's a strong sign you missed an important abstraction. There are three main distinctions between value objects and entities. The first one refers to the way we identify them. There are three types of equality when it comes to comparing objects to each other. Entities possess identifier equality, meaning that we treat two entities as being the same only when they have the same identifier. Value objects, on the other hand, have structural equality. We consider two value objects to be equal if all their fields are the same. Value objects cannot have an identifier. The second distinction is that value objects are immutable data structures, whereas entities change during their lifetime. And finally, value objects cannot live by their own. They should always belong to an entity. In our application, for example, the money value object doesn't make sense without a snack machine. A snack machine composes two money instances. It also means that value objects shouldn't have their own tables in the database. We will elaborate on that topic in the next module. We discussed the techniques for recognizing a value object in the domain model. A good approach here is to compare one to an integer. If they have essentially the same semantics, you can be sure the class you are looking at is a value object. We also talked about an important practice of moving as much logic to value objects as possible. Value objects are lightweight and therefore are extremely easy to maintain and reason about. We looked at the code of the base entity and value object classes, and also saw why we cannot use .NET value types to create value objects. We discussed test-driven development in the context of domain-driven design and two approaches to writing unit tests. We will talk more about unit testing in the following modules. Alright, we've made a good progress here. In the next module, we will see how to introduce user interface and a database in a way that helps keep our domain model clean and isolated.